implementation of a quantifiable circular economy framework, a system engineered to recover resources and decouple medical care from ecological extraction. To fully execute its mandate to protect human health, the healthcare sector must dismantle its linear operations and adopt sustainable infrastructure. This transition begins with Pillar 1, energy-efficient design. The modern hospital is a massive, continuously operating node that demands immediate energy optimization. Peeling back the exterior reveals high-draw systems, climate control, and sterilization. First, AI-optimized HVAC networks use predictive algorithms to regulate airflow based on room occupancy. Second, instead of venting sterilization heat as waste, closed-loop systems redirect it to preheat the hospital's water supply. The final layer of structural optimization requires shifting away from grid-based fossil fuels by installing integrated renewables directly into the facility's architecture. Stacking these architectural and energy interventions yields measurable returns, capable of reducing a single facility's overall carbon footprint by up to 25%. Yet the physical building only contains a fraction of the emissions problem. The true ecological cost lies in what moves through those walls. The vast majority of healthcare's environmental impact arrives daily at the loading dock. Under Pillar 2, Sustainable Procurement, we must address the data showing that nearly 70% of all healthcare emissions are generated entirely by the supply chain. Reversing this trend requires navigating stringent clinical safety regulations, which have historically incentivized the continuous purchase of sterile, single-use plastics over durable equipment. This chart outlines a structured circular healthcare ecosystem, broken down into macro, meso, and micro levels, to systematically bypass these supply barriers. At the meso level, institutions must establish collaborative networks dedicated to the continuous reuse, recycling, and recovery of high-value materials. The most immediate application of this strategy is the validated reprocessing of complex medical devices, cleaning, disinfecting, and functionally restoring items previously categorized as single-use. The viability of device reprocessing is a matter of hard cost emission calculus, clearly demonstrated in recent case studies evaluating flexible laryngoscopes. Researchers utilize this minimization function to evaluate true viability. It compares the number of new devices against reused cycles, factoring in both the financial costs and the CO2 emissions per unit. This chart shows the decline in cost and CO2 emissions across increasing laryngoscope reuse cycles. By mapping the data, we see a steep decline in carbon output. The lower chart identifies the exact optimization point. At 4 reuses, circular procurement mathematically outperforms linear disposability. To Pillar 3, Smarter Waste Management. This chart shows hospital waste composition. Standard medical refuse is heavily dominated by recoverable plastics and metals. The critical failure is extreme overcaution. The chart below shows global hazardous waste averages 15%, while the European Union reports a staggering 25%. Non-hazardous materials are routinely misclassified. When perfectly clean, recyclable plastics are mixed into red biohazard bins, the entire lot is condemned to high-emission incineration. The technological fix requires digital tracking. By utilizing IoT sensors and blockchain technology, hospitals create immutable records of waste streams, ensuring absolute accuracy in segregation. Flawless segregation permits facilities to route clean plastics to dedicated recycling centers, while funneling genuine biohazards into advanced energy recovery systems that convert infectious waste into usable power. Smarter waste management systematically transforms a costly disposal liability into a secure, resource-yielding recovery engine. Optimizing a hospital's internal operations yields limited results if the materials arriving at the loading dock are manufactured through heavily polluting processes. This necessitates Pillar 4, Low-Carbon Pharma, which pushes sustainability interventions upstream to the origin point of medical production. This diagram shows how advanced manufacturing relies on industrial symbiosis to eliminate waste. In practice, these networks link separate sectors. Chemical byproducts from one plant are deliberately captured, safely becoming raw input materials for entirely different medical processes. Concurrently, manufacturers apply the principles of green chemistry to engineer toxic solvents and severe pollutants out of the drug synthesis process entirely. Downstream efficiency will always be constrained by upstream pollution. True sustainability requires pharmaceutical supply chains that are clean by design. Architecture, procurement, waste processing, and pharmaceutical manufacturing cannot operate in isolated silos. This graphic details the conceptual framework required to run a carbon-neutral healthcare sector, combining sustainable supply chains with robust governance. Its execution relies on rigorous, cross-sectoral collaboration between device manufacturers, clinical providers, and regulatory bodies. But implementing digital tracking systems, deploying break-even procurement formulas, and negotiating symbiotic supply chains requires a specific administrative expertise.